locally testable code, which we've already discussed in the past, but I'm going to show a construction using high-dimensional expansion. So remember that we already had a locally testable code in the course, and this was the Hadamard code. So if you recall, this was a code that takes n bits, some string a, and treats it as a set of coefficients, and encodes this a into fa, which is a string of 2 to the n bits. Really, we view it as a string of, as a function from v to 0, 1, where fa at a point x is equal to summation aixi mod 2. Remember this code? And the rate of this code is very small. The length of a code word is 2 to the n, but the dimension is n. Well, yeah, dimension is n. So is this right? Yeah. The rate of this code is, let me call it, I don't know, n divided by 2 to the n. So that's, no, sorry, log n divided by n. So if capital N is 2 to the n, this is very small rate, but it has other very good features. It has constant distance, so the distance is a half. We didn't discuss it, but every two code words differ in half of their bits. And what we did discuss is the fact that it's locally testable. So how is this code tested? The tester for the Hadamard code was choose 2 points x and y, and accept if f of x plus f of y equals f of x plus y. So this tester looks at 3 bits in a code word. And we proved that it works. And when we proved that it works, what we did was we looked at certain constraints, and we saw that they have linear dependencies between them. There was this constraint, if you take x and x plus z, and their sum, which is z, and you take y and y plus z, and their sum, which is z, and then maybe you take x plus z and y plus z, and their sum is x plus y, then these are 3 constraints. Because I call it a constraint because if you query the function f at these 3 points, you expect to get 0. And the sum of these 3 constraints is a third constraint, which is x, y, x plus y, is a fourth constraint. So the meaning, what comes out of this is that you get here a loop of constraints. These are 4 constraints that are linearly dependent. Okay, the sum of these 3 constraints is this constraint. So it means that out of these 4 constraints, either all of them are satisfied, that's okay. If one of them is unsatisfied, there must be at least another one that is unsatisfied. You need an even number of constraints here to be unhappy. So this is this was very useful for us when we proved that that this is a good local test, because we somehow used this fact to show that a certain correction algorithm works. And another way to view it is to say, if you had some unhappy constraint, it forces many other unhappy constraints, and maybe this propagates. So we will see this today again. So the Hadamard code is one example and of a locally testable code, actually the first one that people looked at. And a very natural generalization of this is the Reed-Muller code. If the Hadamard code consists of all functions that are degree 1. We usually don't call them degree 1, we just call them linear. Weizmann code consists of all functions that have degree at most d, where d is some parameter, and there's two variants. Maybe the one that we sort of saw in one of the lectures is when the field, the alphabet size, the field is large and d is much smaller than the field. You can also have a variant where the field is still f2 and the degree is much smaller than the ambient dimension. We're not getting into this. There's a huge literature on these things. The testability of the Reed-Muller code is called low degree test. And it's an important topic, and there are still many open questions here. It's not like we know everything here. But when you look at these codes, no matter how you play with the parameters, with the field size and with the degree and with the number of variables, because these codes are like functions from f to the m to f of degree d. This is the Reed-Muller code of degree at most d. So there's three parameters here. There's the field size q, there's the number of variables m, and there's the degree d. No matter how you play with this, you'll never get, you can get constant rate if you take the degree to be very large and m to be small. But you will then not get testability. The local test will not be so local. You will have to read relatively many queries. You can have it be very locally testable if you let the degree be very small, like 1, but then the rate will be very bad. So you cannot combine these two things. You'll never get both constant rate and constant locality, meaning that the test looks at only a constant number of symbols. So these are these algebraic codes, and there's many other locally testable codes. I'm not going to give a history here. But anyway, a natural question that one can ask is, are there error correcting codes with constant rate and distance? When I say constant rate, I mean relative rate, and constant distance, relative distance, and locality, also constant locality, and constant locality. And when I say locality, what I mean is that there is a tester that tests these codes with a constant number of queries. And I'll now recall the definition. I think we saw it, but I want to define it again. So this is the question we want to address. And let's write the definition. A linear, I mean, actually the definition doesn't need linearity, but we will only talk about linear codes today. A linear code C is a Q beta locally testable code if there is some parity check matrix. So let me call it R by N parity check matrix. Okay, so let me draw it. So this is N and this is R, and this is my matrix H, such that C is the kernel of H, meaning it's the set of strings, n-bit strings, such that multiplying on the right gets you to 0. Okay, so W is an n-bit string. I multiply it, I need to get 0. So it means really that I'm thinking of every row in this matrix as a constraint. When I do this matrix multiplication, I put W on every one of the rows, and I need to, if I have ones here and zeros everywhere else, then I need to read these bits in W, XOR them, and see that it's 0. Okay, so it's locally testable if there is some parity check such that, well, first thing I want is that each row has at most q non-zeros, so that each check is local. It only looks at up to q symbols in W. And the second thing is that this is the local testability. I want that for every W, there is a relationship between the distance of W from the code and how many checks succeed or don't succeed. So okay. So here I wrote the weight of HW. HW is an R-bit string. It's the syndrome. It really tells me which check succeeded and which check didn't succeed. And the weight, I mean normalized. So it's a number between 0 and 1. It's the number of ones divided by R. So this needs to be at most beta times the distance, at least the distance is bounded by the weight, W and C. So the way to interpret this inequality, and we've seen it throughout the last lectures, there's a relationship between the distance from the code and how many tests reject. Okay, so if W is inside the code, the distance here is 0, and the weight here will actually also be 0. If W is outside of the code, then we want that if it's far, then there will be many tests that reject. This is our definition. So let's make some remarks. So the first one is the definition is equivalent to having a property tester for the question whether is W inside the code. What is a property tester? It's a randomized algorithm. It does the following. The tester is an algorithm that does this. First, choose a random row, so maybe a random number between 1 and R. Okay, and then read and then accept if and only if summation. Okay, I goes from 1 to n. Wi times HRI equals 0. So the way this is written, I need to ask myself how many symbols am I reading from W, because it looks like I'm reading n symbols. But really this is just the same as saying summation over all the i's where HRI is non-zero of Wi. And if we were over a larger field, then, okay, I can add here HRI, that's okay. But I don't need to sum all the other ones, right? So if this is bounded by Q, I'm reading only Q symbols in W. Okay, and it's clear that, it should be clear that the probability that the tester rejects is exactly the weight of HW. So the inequality shows that if the tester rejects with small probability, it means that W is close to the code. And if W is far from the code, the tester will reject with probability the weight divided by beta. Okay, that's remark 1. So this is a connection to property testing. And the remark 2 is that there is a cohomological viewpoint, which it repeats itself, but I will repeat it anyway. And really this definition is like saying that there is some chain that has good coboundary expansion. Question? No. So what is the chain? So really you can look at this chain. Start from the message space. Then there is some generating matrix that encodes messages into code words. I don't care which one, as long as it generates the code. And then there is the parity check matrix, which takes strings and computes how they do on all these constraints. Right, so this is a two chain. When I say that something is a two chain, what I need to check is that the image of the first map is contained in the kernel of the second map. In this case, it's equal. This is how we chose G, so it's not interesting. Anyway, what does consystolic expansion of a two chain mean? It means that we defined it this way. We said that the H, the consystolic expansion of this chain, was defined to be the minimum over all W that are in 0, 1 to the n. The W's live in the middle. 0, 1 to the n minus kernel of H or the image of G. Let me say the image of G. This is just the code, yes? And then I'm minimizing over this quotient between the weight of HW and the distance of W from the image of G. This is coboundary expansion. And really, I shouldn't, we called it H, but really it's clear that, that it's beta. So if a code is a beta LTC, if H So the only difference syntactically between what's written here and that inequality is that here we are minimizing over W's outside of C. But if this is because we have something in the denominator, it cannot be 0. If I multiply the distance on this side, then for every W I need that this is the constant beta times the distance is at least the weight. Okay, is at least or at most weight. So for every W, this is at least H. For every W, this divided by this is at least H. So the weight is an upper bound on beta times the distance, which is exactly what's written here. You see that? Okay, so we have this nice cohomological viewpoint on this local testability.
In the cohomological viewpoint, you didn't mention the local one. Right?
Thanks. Right. So the way I described it here, just the expansion doesn't say anything about locality. If in addition H is is local, then you get this systolic expansion with this extra locality. So in this terminology, locality is not built into this terminology, you need to specify it. Also in the LTC-ness, you add 1 and 2. So 2 is equivalent to this. Okay, now we want to recall expander codes. So I don't think we talked about them enough, so I'll talk about them today. So if we have a graph that's an expander graph, so we imagine a graph on many vertices, but it's very sparse, it's deregular, and suppose it's a lambda expander. Meaning that the second largest eigenvalue normalized is at most lambda. So we're given such a graph, and suppose we're given two things, this graph, and we're also given a code, a linear code. But it's not a very big code, it's a code only on d bits, so it's a constant, like 10. A linear code with distance delta 0, say, and rate r0. Okay, so rate r0 means that the dimension of C0 is r0 times d. Okay, so we're given these two objects, and from them we construct a new linear subspace, the expander code. So question? Okay, and what is this linear subspace? So if we draw the graph here, this is G, I have a vertex, so the subspace will actually be subspace of one chain, so it's going to be labels on the edges, and the way we're going to put linear constraints on them is that we're going to constrain edges that surround this. For every vertex we look at the set of edges here and constrain them to be inside the code C0. So suppose with parity, suppose C0 has a parity check matrix H0, then I can look at the matrix. I'm now constructing a parity check matrix for my new code. The number of rows here is the length of the code, so it's going to be E. This is my block, the length of my code words. And the number of, that's the number of columns. The number of rows is going to be, for every vertex, I'm going to have 1 minus R0 times D. So this is these are how many constraints my parity check H naught has. Right, because this is the codimension of this code. Okay, so, I mean, this can have redundant constraints, but assume it's not redundant. Assume it's a non-H0 not redundant. So it's 1 minus R0D by D. Okay, so now for every vertex, so suppose this is a chunk for the first vertex, V1, and then I have another bunch of rows for V2. How many rows? This many. And what am I going to do in these rows? I'm going to look who are the neighbors of V1. So imagine this guy is V1. These are the neighbors of V1, these edges. So there's some columns here that correspond to these guys. For simplicity of drawing, I imagine that they're consecutive, but of course they don't need to be consecutive. And then we just plug in here a copy of H0. Okay, and then I look at V2, and I have a bunch of edges, and maybe they're located somewhere else, here. So I plug another copy of H0 here. And in general, of course, it won't be consecutive. There will be a part here, and a part here. And, you know, it will be like H0 is is plugged in there. So this is how the parity check matrix looks like. And if you want to get a better definition of the code that looks a bit nicer, you say that it's just all functions on the vertices or one chain, on the edges or one chains, such that for every vertex, when you look at your function restricted to EV, so I'm using this notation to denote all the edges that contain V, then what you see belongs to the code C0. So this is our definition of an expander code, and this definition is due to Sipser and Spielmann, and what's nice about it is that you can easily prove that it has all these nice properties. So let's see. Firstly, the rate. If R naught is bigger than a half, then the dimension of C is linear in the number of edges. So as long as the local rate is slightly bigger than a half, you already have a lot of code words. A priori, you define the code by a bunch of parity checks. It could be that only the zero function survived. But in fact, a lot of code words survive, and let's see why. So the degrees of freedom here, so I have a bunch of linear constraints. So how many degrees of freedom do I have? I have this many bits. This is a priori the dimension of my space. How many constraints do I have? So if I look at my parity check over there, really what I'm claiming is that this matrix doesn't look like I drew it. What I'm going to claim is that this matrix looks like this, that there are more columns than there are rows, and therefore it's not full rank. This is what I'm now going to claim. So the number of degrees of freedom is E, but the number of constraints we wrote, it's V times 1 minus R naught times D. I'm just copying from over there. And so, but E itself is V times D over 2, right? So if I subtract, I get V times D over 2, and then I get 1 minus, this is V times D over 2 times 2. So I get that this minus this is at least this much. And of course, this is a lower bound on the dimension of the code. So if R naught is bigger than a half, this is bigger than 0, and I get that there's significant rate. Basically, just by counting constraints. What about distance? So, anyone remember? We talked about this at some point. Unless you already know, then you shouldn't speak up. So far, what did we do? We took some local subspace, we planted it, how, just using this graph, and maybe it's an expander, maybe it's not an expander. And now I'm saying, you know, actually this system of equations defined like this gives me a subspace with a large distance. Now, why would it have large distance? This is kind of already using the kind of interesting power of expansion. So if you want to understand it, think since the code is linear, it's enough to look at, to bound the weight of smallest non-zero code word. Smallest weight non-zero code word. So suppose I have some non-zero code word. So it's basically I'm labeling the edges by zeros and ones. Can it be that this code word has very few number of ones? Any idea? Okay. So a lot of you know this and you don't want to say. Okay. So once you have a single non-zero edge anywhere, immediately it means that the local view of this vertex sees something non-zero in the code C0. And we already assumed that the local distance is delta 0, so it means that not only one edge is non-zero, in fact a delta 0 fraction are non-zero. So what this means is that if I denote by V prime the set of vertices such that V sees a non-zero edge, you know, maybe it looks too redundant that I'm doing this proof, but it will serve me soon when I talk about the LTC, so I want to do it in details. So I'm looking at all the vertices that see some non-zero edge. And my claim is that each V in V prime has many other neighbors in V prime. How many? At least. Thank you. Thank you very much. Yeah, so if it sees one non-zero, it sees delta 0 times d non-zeros, and that means that each one of the endpoints of those edges also sees a non-zero. So it means that every guy in this set has many neighbors inside this set. Okay, so then we have this Alon-Chang lemma, which I think we at least stated in the first lecture, that says that if G is a lambda expander, like I'm assuming, and if V prime is a set of vertices such that the subgraph induced on V prime has average degree delta, then the cardinality of V prime is at least delta minus lambda times V. Meaning, if you have a subgraph that with delta probability you have a subset of vertices that with probability delta you're not getting out of it, this set must be very large. So if delta is smaller than lambda, you don't get anything, but once delta is above lambda, you become linear. Your set becomes linear. So what does this mean to me? It means that the distance is at least delta times delta minus lambda, because I know that I have at least this many vertices that see non-zeros, and each one sees at least a delta fraction of non-zeros. So this is lower bound on the fraction of edges that are non-zero. And actually this cannot be improved. So
should it be divided by 2 for double?
Yeah, it's tricky, but no. Think of it as a probabilistic process. I first select a vertex. With this probability, I land inside V prime, and then I select a random neighbor. Probability delta, I land on a non-zero. The reason this cannot be improved is because a tensor code can be viewed in this language as an expander code. And in tensor code, we actually know that the lambda is 0 in that case, and that the distance is indeed delta squared. So that's it. Okay, so that's nice, the distance and so on, but I want to also talk about decoding of this code. Again, as a warm-up towards talking about local testability. Okay, so maybe I talk about it here. So now, please speak up, don't restrict yourself even if you've seen these things before. Decoding, okay, so now what does decoding mean? Suppose I'm given some word W, and suppose I'm told that there were a few errors in W, so that I'm promised, say, that the distance of W to the code is small, I don't know, some epsilon, okay? And now I want a decoding algorithm. I want to come up with an algorithm that recovers the code word that's closest to W. So how would you do it? Think of W as written on the edges, and you need to now find the correct code word.
If there's a vertex where more than half of things are violated.
Okay. If there's a vertex where more than half, so remember the bits are on the edges.
Right. I guess you want an edge where more than half of the constraints are violated.
Okay, I mean the edge can maybe have 2 constraints on it. I don't know how many constraints it has on it. Maybe more. So, but okay. So one algorithm is to say for every edge, maybe think of it in this matrix. An edge is one of the columns. You look at all the constraints touching it, so you know if there's 0 here, you don't care. But there are a few constraints that touch it, and if more of them are unhappy than happy, maybe you will flip this edge. But it could be that there's only too few constraints on this edge, so I'm looking for something, a variant of this, not this. So let me tell you my first step, and then we can see if we can continue. So my first step in my algorithm is every vertex finds a local view closest to the received word, to W restricted to EV. Okay, let me call this local view WV. So what I mean is that every vertex sees D bits around it. Maybe what it sees is a perfect code word in C0, so it will choose WV to be this code word. Maybe it sees something that's close to a code word, so it will choose that. So it will choose some code word. WV is always going to be in C0, such that yeah, it will choose the closest one. Okay. Now, if the given word was a perfect, there were no errors, then of course WV will be the same as what you saw, and there will be no problems. But once there are errors, what kind of things can happen? It could be that the errors are distributed kind of very benignly, so that every vertex will only see maybe 1 or 2 errors. There will be some error here, some error here, some error here. If the error pattern was like this, then this vertex, out of the D bits, only 1 bit got flipped, so the nearest code word is exactly the word that will correct this error. And every vertex that only sees very few errors, less than delta over 2, will reach the correct code word after this one step. Okay, so if the error pattern was like this, we are done after this one step. But when will this actually fail? Okay, so if some vertex had so many errors like this, maybe I can actually correlate my errors so that I put here some false code word. Let's say I put all zeros here. Okay, even though it's not the 0 code word. Then it could be that, okay, I did that, but maybe after one step these guys will all be corrected, all the neighbors of V1, and then we're almost home. All the neighbors of V1 got corrected, but V1 he saw zeros, so he's going to be 0. So what I would like to do next is to somehow have some message exchange between the different vertices that have these local views, and say every vertex, if he looks around and he sees that all of his neighbors think something, maybe he wants to change his mind. Okay, so my next step. So what would I do the next step? So now I'm going to say arbitrarily order the vertices, arbitrarily order V, and then each vertex looks at opinion of neighbors and switches local view if higher agreement. So what I mean by this is that the vertex looks at its edges, touching it. Every edge, the neighbor also has an opinion about that edge. So let's collect all the opinions. Maybe I get something that is close to some other code word, not to the one I have. Then I will switch. And the measure that I'm going to measure is this. Okay, I'll write it in another place. So I'm going to look at the set of disagreeing edges. So it's all the edges UV, such that the local view of U at point V is not equal to the local view of V at point, well, I should say UV and UV. Okay? These are all the edges of disagreement. The local view here thinks differently than the local view here. Okay, and so what I'm going to do is that a vertex already disagrees with some of its neighbors. Maybe it can find a better local code word that will reduce this disagreement. If so, you will do it. Okay, and we'll just repeat. Repeat until stuck. No, repeat. Okay, repeat until you have no more moves. No one wants to switch. And now, finally, if perfect agreement output W hat. So perfect agreement means that all the local views agree with each other, and then I know what to do. I know how to define W hat. For every edge, I can either take the value from this endpoint or from that endpoint. They agree anyway. And what I will get is an honest code word, because the restriction to any local view is in the local code. So is it clear that if I have perfect agreement, I found some W hat? Okay, so now you need to prove some things. Kind of the most, okay, so what kind of things do you need to prove? So firstly, we can ask, does step 2 terminate? What do you think? I'm looking not for a yes/no answer, but for some reason.
If you increase agreement every time, if you can, then eventually you're going to hit 100%.
Right. I can look at this set E prime of all the disagreement. It's a set whose size is at most E, right? So it's bounded. And every time I run this loop, I reduce this disagreement. So I can only run this many times. Definitely, I will terminate. Okay, so then I can ask, does it terminate? Does step 2 terminate with perfect agreement? It could happen a priori that I do this, and at some point there is some disagreement, but every vertex, even though it disagrees, there's no better choice for it. It's stuck. This could happen. So what we need to prove is that we're not supposed to be able to decode at all costs. We're only supposed to be able to decode when the number of errors was small. So what we need to prove is that if the number of errors was small, then you reach perfect agreement. Okay, so why would that happen? Yeah, so before even I talk about that, I just want to say, without kind of getting into the details, that suppose we do terminate with perfect agreement. We will show it later. Does it mean that we succeeded in decoding? So we will have a lemma. We will have a lemma that if number of errors is small enough, then we get perfect agreement. Okay, but suppose we already believe this lemma. Why is this good for us? I mean, it means that we will find the W hat. Now, maybe W hat is the wrong code word. How do I know that W hat is actually a good code word? So the thing is, how many steps am I making here? The number of steps I'm making has to do with the number of disagreements. And the number of disagreements, when can two vertices disagree? Only if at least one of them sees the wrong local view. Okay? So if I keep count of how many vertices have the wrong local view, and if this number is not too big, it means that this set will be not too big. It will be like epsilon. Okay? And then it means that the number of times I run this loop is only is very small, like epsilon times the number of vertices. And this will mean that W hat can only be different from the original word W on edges that touch one of the vertices that ever saw something wrong. If a vertex was right and it kept being correct all the time, then W hat will be the same as W. So the only places where W hat will be different is if it touches some vertex that was incorrect. And so how many vertices are incorrect? Well, there's the number of vertices that were initially incorrect, plus the number of times we ran this loop. Every time maybe we made some other vertex incorrect. Both of these numbers are some epsilon times V, and so you get that W hat will be correct. Now I have to say, this is not the analysis that people usually make for decoding expander codes. There's a much better analysis. I mean, when I say much, I mean the parameters come out better. You want to decode from the largest fraction of errors that you can. So you really want to do it from delta, from the distance divided by 2. And this is far from that. But this is very similar to the analysis we will see for local testability. And I mention it because it's a nice question whether the analysis of local testability can be improved to get better parameters, just like this can be improved. I mean, no one ever considered this. They already considered the improved thing. But anyway. Okay, so let's see why the lemma is true. I think this is the most interesting to understand why the number of errors kind of cannot be large. If it was small, then it will decrease to 0. It cannot be stuck. And the reason is very simple. Let V prime be the set of vertices that see, let me be, that see an incorrect view at the end of the algorithm. I think that's the point. Yeah. Okay, WV is incorrect at okay, so I ran the algorithm, I got stuck, and now I have a collection of local views, and for those that have the incorrect local view, I want to look at them. And now what I'm going to do is similar to the argument that we did for distance. If if V is an incorrect local view, what can you say about its neighbors? Can it be that all of its neighbors have the correct local view? No, why not?
Incorrect means it disagrees with neighbor.
Okay, thanks. For decoding, we are assuming that we got some W, and its distance from the code is small, so there is some correct W0 that is in the code, and W is just epsilon away from it. So when I say correct, incorrect, it's with respect to this ground truth, W0. Okay, so now I'm looking at the vertex, and I see that the local view is incorrect, meaning it's not like the local view of W0. Then, Tal, you were going to say?
Sorry, can you repeat the question? Just because I lost it.
You asked okay, so if V sees an incorrect local view, can it be that all of its neighbors actually see a correct local view?
No, because that edge is incorrect, and they have corrected it.
Okay.
If all the neighbors were correct, V would have corrected itself to the correct.
In the algorithm, in this step, if all the neighbors were correct, it means that the neighbor's opinion about this guy V would actually be a nice code word. And V would say, if I flip to this code word, I will improve the disagreement. So V would improve. So the fact that V didn't improve means that many of the neighbors disagree. In fact, it means that at least delta over 2. So I'm saying, if V is in V prime, then at least delta over 2 neighbors are in V prime. Because this argument is also true if fewer than delta over 2 were incorrect, because then there's only a unique code word that's closest to V, and it would be the correct one. So we get again the same thing that we had before with the Alon-Chang lemma, where you have a set V prime. For every vertex, you have many neighbors that are inside this set, but you're in an expander, so it means that the set must be large. Okay, so once I get that the set of incorrect vertices is large, it contradicts the fact, I'm not going to do all the details, but okay, so this means that V prime must be large by expansion, So this, once I get that V prime is large, it contradicts the fact that I started from a word that has very few errors, right? Because we said the number of vertices that ever see an incorrect value is bounded by the number of vertices that initially see an incorrect value, which is bounded by epsilon, plus the number of steps, which is also bounded by epsilon. So without going into the details, this means that this, for small enough, this is a contradiction. Epsilon here is the number of errors, the number of the amount of noise. Let me just write noise. So sketchy proof for the fact that if there is some epsilon such that if a word had epsilon of its bits flipped, this algorithm would recover the correct code word. Okay. Good. So let's take a break. But I just want to say one thing, which is when. Yeah, please.
For the definition you gave for the locally testable codes, we don't even need the decoding algorithm.
Correct. It was just kind of a side. We don't need decoding. We didn't talk about decoding at all for locally testable code. Of course, it's a very important feature of a code that it's decodable. Okay, one thing, notice that so we talked about expander codes, we made this definition, and then we discussed rate. It was done by counting constraints. Then we discussed distance. It was basically done by using the distance of the local codes. And we did decoding. Nowhere did we use the fact that all the local codes were the same. Really, I could instead have CV, where for every V, CV was a different code on D bits. Everything would work the same as long as the distance of CV is at least delta 0 and that the rate and the rate, the dimension of CV is at least R0 times V. So this is more general. You don't need to have the same code everywhere. You can have different codes in different places. Okay, let's take a break, and then we talk about the question, are expander codes locally testable codes? Okay, are they? Okay, we'll see. Bye. Okay, as now we want to ask, are expander codes locally testable codes? We already saw that expander codes have constant rate and distance. Okay, so we already saw that expander codes have constant rate, constant distance, and constant locality. So they are LDPC, low density parity check, right? Because in the parity check matrix, we have every row has a constant number of non-zeros. That's nice. But are they locally testable? So I already tell you, of course, if we knew that, then I wouldn't have all this introduction. So the answer is generically no. And when I say typically no, what do I mean? I mean, expander codes is not something, is not one thing. You give me a G and you give me C0, and then it gives me a code. So sometimes yes, but sometimes no, or typically no. So let's try to see why. Why is that? Okay, so consider a family of CV error correcting codes. Sorry. So I'm going to have for every vertex a different little code, local code, and I'm going to define. Let me call this, some family of local codes, and then I'm going to look at the code C, which is the code of the graph G and this family C. Okay, so it's basically, instead of C0, I just write here it's CV. And this is I'm going to denote it the code of G and the family C. So now, if each of these guys has distance delta and the rate is R0, I get here a code with constant distance. Now I'm going to change it a little bit, fix some V, V, some specific guy, and let me just call him V, and change and increase CV by one dimension. So basically we define C prime V to be a super code of CV such that the dimension is one bigger. And suppose we do it in a way that still, even for this guy, even though it's a bit bigger, still it has distance delta, the rate is going to be bigger, so that the new family C prime is now the same as C, except CV replaced by C, V prime. In other words, basically what did I do? I took one of the vertices and I erased one row in the parity check matrix. This is all I did. Now I have a new parity check matrix that's the same as before, except I erased one row. Which row did I erase? I looked at the chunk corresponding to this guy V, and I increased its dimension by one. So maybe I did it by erasing one of the constraints. Okay? Okay, so now this new code has the same properties as the old code. All the local codes have high distance, so the entire code has high distance. So it means that the new code, let me call it C prime. So, and C prime is the code of G with one row erased from the parity check matrix. Okay. So what I can say is that this the code C is certainly contained in the code C prime because it's the kernel. This guy is the kernel of a smaller matrix, and it could be that in fact it's actually bigger. It could be that they're the same. When are they going to be the same? I took a matrix, I erased one row, and now I look at the kernel. When is the code going to be the same?
There was a redundancy.
Exactly, if this row is already linearly dependent on other guys. But if all the rows are linearly independent, then this is strictly larger than this guy. In that case, I can take some word that's in the kernel of C prime, a word that's in C prime and not in C. Okay? So take this W in C prime that's not in C. What can you say about how many constraints are violated on this W? How many constraints of C? So fix some W in C prime minus C. And now you ask, now you look at the parity check matrix of C. So without the row erased, so the row is still there. Well, on all the other rows you get 0. On the erased row, what are you going to get? 1, thanks. Because if you got a 0, you would be in C. The fact that you're not in C means you must violate some constraint. Okay, so you violated the red constraint. So what is the weight of HW? If this is the matrix H, it's 1 over the number of constraints. Let me call them R. So it's 1 over R. Basically, it's the smallest it can be. For any string that's not in the code, the weight is going to be non-zero, so the weight is going to be at least 1 over R. This one is as close as you can get to being a satisfying string. Okay, so it satisfies all the constraints except for 1. So it really pretends to be in the code. So if it were a locally testable code, what would it mean? It would mean that if a word satisfies so many constraints, it must be very, very close to the code. However, W is in C prime. C prime itself is a code. That means that every string in C prime is far from any other string in C prime. And in particular, C prime contains C, so W is far from every other string in C. The distance of C prime is at least delta times delta minus lambda. So the distance of W from any, W is not in C, so the distance here is not 0. From any other guy in C is at least delta times delta minus lambda, which is huge. It's a linear, this is a linear fraction. It's a constant fraction, and this is a tiny number. It goes to 0 with R. So this is like the strongest possible violation of being locally testable. The distance we want, for LTC, we want that the weight is bigger than beta times the distance. Our weight is 1 over R. Our distance is some delta minus lambda. So the beta we need is something like 1 over R, right? Times delta minus lambda. It shows that this gives you an upper bound, a very, very tiny number on the possible beta you can get. Okay, so does this mean that all expander codes are not LTCs?
Really? I think you have this property where if you take something out, you maintain
Thank you.
distance.
Okay, the only thing that I was using here is that when I erase this red row, I gain some new W. And like people also said before, if there's redundancy, then I wouldn't gain. I erase a row, the code stayed the same. Indeed, if this happened to be the parity check matrix of the Hadamard code, and I erase a row, what would happen? Nothing. It would stay the same code because there's so much redundancy over there. So in expander codes, it turns out, I mean, you need to work, I didn't show it here, that many cases you can choose these guys so that they're all linearly independent. And then there's no LTC. Okay, so generically you don't get LTC. So what we want is to add one more dimension. And this will help us to get the LTC-ness. And remember, I said in the beginning of today that, remember, the Hadamard code, they had these constraint loops. I forgot to say, so I'm going to say adding one more dimension. One more dimension. So remember that we had these constraint loops on the Hadamard code. Remember also from last week, we had these consystolic expansion, where we had a one-chain f, so it gave values on the edges, also this edge, I don't know. And our tests for being a cocycle were the triangles. So the constraints were these triangles, and the pyramid was a loop on the constraints. These 4 different constraints sum up to 0, and we said, that means that if one of the triangles is unhappy, another triangle is unhappy. So we had this constraint loop, just like we had in the Hadamard code. So we want to build a code that has these constraints and that they have loops among them. And when we build the expander code, it's not clear how to get them to loop around. Okay, but if you look at the cohomological statement, then you had this thing where you had 0, 1 to the n, and then you had the parity check, 0, 1 to the r, and the loops were things of this form, 0, 1 to the, I don't know what number, L for loops. Okay, so basically what you want is you have a parity check here, and then there's another arrow that shows you there's some more redundancy among the constraints. And in the expander code, what we had is 0, 1 to the x1. This was, our code words were defined on edges. And the checks were on the vertices, but every vertex had some number of checks, 1 minus r naught times d. Let me just call it some number of checks per vertex. That was in expander code. And if we want to have a 2-chain, a natural idea would be to say, okay, let's put the bits not on x1 but on x2. Then I can put the checks not on x0 but on x1, maybe times some m1. And then I'm going to also have loops, constraint loops, on x0 times m0. Okay, so this is kind of a natural thing, a natural hope to get something that looks like the Hadamard code but uses the infrastructure of high-dimensional expanders. The thing is, using the simplicial complexes, I don't know how to do it. We don't know how to do it, although it looks like it should be possible. So instead, what we do is we introduce a two-dimensional object or expander, but it will have not. It won't have triangles. It will have squares. And somehow, using this guy, we will be able to construct such a chain and construct such a code. Okay, so this is what I want to talk about. First, I want to talk about this structure X, and then I'm going to talk about the code. Okay. Yeah.
In terms of just motivation for why adding the additional dimension, you want to have the redundancy in order to prevent this red line situation that you showed before.
Right. I want the constraints to have redundancy. Maybe the best way to think about it is when we talked about the consystolic expansion, we said, suppose we start with one problematic triangle that that is not satisfied, then any pyramid that sits on top of this triangle will have another problematic triangle. So you're showing that if you have one problematic triangle, you're going to have many other ones. So this reminds us of the same situation we had here, where you had one problematic edge, you had many, or vertex, you had many other ones, and this kind of propagates. So these loops of constraints allow us to propagate the unsatisfied constraints. You won't be able to have just, here you had just one unsatisfied constraint. If you have these loops, then this one red guy will imply other red guys, and those will maybe imply other red guys. So you need them not only to be in loops, but you want that the loops have this expanding structure so that it propagates.
But you don't want to have, if the loops don't propagate, then it will hurt the rate, right? Because the code word will be too.
It's true that if I have too many constraints, it will hurt the rate. But if the loops don't propagate, I won't be able to argue. I want to argue that if you're a code word that violates one constraint, you must violate more constraints. So this is where I want the propagation. But okay, yeah.
Sorry, is it correct that what's stopping you in the simplicial case is that here you really need to be going sort of the systolic direction instead of the co-systolic direction, and then the systoles are small?
I don't think so. Don't think so at all. It's look, if you think of this chain, these are the triangles. You're going to put constraints. Every edge will say the bits on the triangles around this edge need to be in some code. That's fine. But now, so it's easy to define a code like this. Think of a two-dimensional simplicial complex. You think of two chains, so every triangle is getting a bit, and you're going to define your code by, for every edge, you're going to put some local code C sub E that says, okay, this edge looks at the triangles around it, and it requires these bits to be in some local code. This is the most natural generalization of the expander codes. It's fine, it gives you a code, but why do you think you will have loops among the constraints? So you need to understand why does the two-dimensional structure give you loops? The hope was that you would look at a vertex, and this vertex touches many edges. Every edge, all the triangles around it were in some code, so you want that these different codes interact with each other, and there's some loops here. So you define the code by defining the code on the local parts, and now you're going to look at the code from the point of view of the vertex, and somehow you want whatever this vertex C to be an LTC, and that's the part that I don't know how to do. Let me even spend a couple of minutes on this. If I define the code, if I have a simplicial complex X, and I put the bits on and I put for every edge, I put some code CE that I choose maybe arbitrarily. Suppose every edge, there's D triangles around it, so CE is some subset of 0, 1 to the D. That's fine, it's a valid thing to do, and I get some subspace of two chains. What does it look like from the point of view of a vertex? A vertex can look at its link, so the vertices, the neighbors are the vertices in its link, and every edge in the link, so forget about these guys for a minute. Every edge in the link used to be a triangle, so I can, from the point of view of a fixed V, I can now look at what's going on in the link here. And what I get here is an expander code. Do you see this? Because this edge from, suppose this guy is U. This edge from V to U had some code C sub E. So now I think of it as C sub U because V is fixed. And it's just saying that the bits on the edges around U inside this link need to be in this code. So it's really an expander code here. Okay, so you define the two-chain, a code on two chains, and the way you define it is that for every link, really what you have is an expander code on one chain. That's nice, but somehow what you need is that these codes themselves are locally testable. And if this is just a generic expander code, it's not going to happen.
Does it imply systolic expansion? Like if you find somewhere that this does work, does it imply systolic expansion?
Why systolic and not cosystolic?
You're mapping down.
Okay, sure. Well, sorry, you're right, but since you add these guys, yeah, it does. It's the same as systolic expansion, but it's.
Somehow I thought there were arguments about like systole sizes of mapping down complexes that like ruled this out. Maybe they're.
No, I doubt that. I really believe that this can work. It'd be very interesting to see reasons why it can't. Okay, so yeah, so let me just move to talk a little bit about these square complexes. Okay, so suppose G is some group, finite group, and maybe it's good to think of 2 by 2 invertible matrices over some large prime field, if you want. But I'm not going to be explicit about the group. Just there's going to be some group, and let A be some generating set. So just a bunch of elements from the group, and then the K graph. For every group and every set of elements, you can define this graph where the vertices are G. So you have a vertex for every group element, and the edges is the set that connects G to AG for every G and every A. Okay, and really I should have written directed edges because it's not necessarily an undirected graph. If I moved from G to AG, I'm only allowed to move from AG by multiplying from the left by some guy in A. If A inverse happened to be in A, then I can multiply by A inverse and I get A inverse AG, which is G. So if for every A in A inverse is also in A, I get an undirected graph. Okay, so let's write it. Okay, so by the way, and now you can ask if this graph is an expander, and it's a fact, it's a celebrated theorem actually, that there are infinite families of Cayley graphs, in particular of those 2 by 2 matrices. There exist bounded degree Cayley graph families with optimal expansion, optimal spectral expansion. So actually the best Ramanujan expanders are built as Cayley graphs. So really you can think of the graph as being, the group can be very, very large, but the set A can be very small, like size 10. Okay. And by the way, if you want that, the set of generators is small, but the group is huge, you cannot have the group commutative. It cannot be that A times G is the same as G times A. This is because you can just count how many different words you can form with the generators. Since it commutes, there's much less words like that. And so the number of generators must be logarithmic. But we want expanding graphs, so we're going to think of non-abelian groups. And then there's a matter of, are you going to do left Cayley graphs or right Cayley graphs? So what's a left Cayley graph? Where you multiply from the left. And of course you can define the same from the right. So these are two definitions. There's no difference. In fact, there is a morphic under the graph isomorphism that sends G to G inverse. It's not important for us. So this is a graph, but we can combine both sides. So we can define the left-right complex. Let me call it with G and A and B. Okay, so it will be the vertex, well, let me call it x0. These are the vertices, are just going to be the group elements. The edges are going to be two types, the A edges and the B edges, where these guys are going to be GAG, and these guys are going to be GGB. And I forgot to say that A and B are two symmetric sets of a group of generators. You can do it with the same set twice, or you can take two different sets. And let's assume that it could be that this edge from G to A times G happens to be equal to G and G times some other B. So G times B might equal A times G. But let's assume that this doesn't happen. You can choose groups so that this never happens. Okay? So these are my edges. And let me also assume that the sets have equal size, and I'm going to call it D. So in this graph, so I have here a graph with two kinds of edges. Every vertex has D edges of one type and D edges of the other type. And now I'm going to define also two-dimensional faces, which are not going to be triangles, they're going to be squares. But before, let me just say what a rooted square is. So a rooted square, I denote it by AGB. It's just a triple of an element from A, an element from G, and an element from B. And what is it? It's the cycle from G to GB to AG to AGB. So notice that I can take a left edge from G to AG, and then a right edge from AG to AGB, or I can take a right edge from G to GB, and then a left edge from GB to AGB. Okay, so I'm always going to have these four cycles in this graph. And so this triple defines for me this cycle where this vertex is special. Okay? But this cycle can be seen from different points of view. For example, from the point of view of AG, I can think of G prime as being equal to AG, and then I write G prime here, and the A move I need to take A inverse. So I'm going to, let me just call it AG, A inverse, and B. So for example, what is this cycle? It's the cycle where I start from AG. I can either go to AG times B, or I can go to AG times A inverse, or I can go to, which is G, or I can go to GB.
You assume that A and B are closed over inverse.
Yeah, I'm always going to assume that.
Oh.
So we assume, yeah, we always assume that. It'll be symmetric. So this is the cycle A inverse AGB, and this is the cycle AGB, and the special guy here is this, but it's the same cycle. You see, it's just look at it differently. Maybe I should have drawn it. I didn't draw it nicely. Yeah, let me change it. I want. Oh, okay, doesn't matter. It's the same cycle with the same 4 vertices, but the vertex that's highlighted is this guy. Okay. Who else can I draw here? I can also draw GB with B inverse and A, and also AGB with B inverse and A inverse. So basically, in this cycle, there's 4 vertices I can highlight, so I can put them in the middle. And then there's always going to be a choice of generator here and here that will lead to the same exact cycle. Okay, so we're going to not look at the set A cross G cross B, A cross G cross B. This is the set of triples, of rooted squares. Instead, we're going to look at the set where you identify these 4 tuples together. So you only care about the cycles without the root. So the notation for this is like this. You take the quotient, basically you define an equivalence class to be the set of these 4 guys. And I can write that this is equivalent to this is equivalent to this, or I can write that this equivalence class is equal to the set of these 4 rooted squares. Okay, so then you can think of my set x2 as the set of sets, the set of equivalence classes. But we understand that it's really just these 4 cycles where you don't care where you started. Okay. So this is a notation, and this guy is equal to AG A inverse B. Okay, it's just different names for the exact same element. Okay, so that's my my complex. I defined the vertices, I defined the edges, and I defined the 2 faces. And let's look now at an edge and see who are the neighbors of this edge. So suppose I have an edge, I'll call it AG. This is the edge that goes from G to AG. And I can also look at the edge GB, which takes me from G to GB. Okay, so this is notation. So on this edge, who are the triangles? So for every B, G has some neighbor GB. AG also has some neighbor AGB. And there's going to be a square, right? Because these guys are neighbors through A. So in fact, for every different B, I'm going to have such a square, right? So here's another B. This is GB prime, and this is AGB prime. And maybe there's another B, GB double prime, and AGB double prime. So in general, around an edge of type A, I have a book of squares of type, one for every element in B. And if I look at this edge from G to GB, then I have the same thing. For every A, I will have, I will have A different squares corresponding to the different A's. Okay. What about a vertex? If I have a vertex G, what does the neighborhood of G look like? So who are the neighboring vertices? So have maybe A1G, A2G, A3G, and more. And I'm also going to have B neighbors, so maybe GB1, GB2, GB3. Right, and now, so who are the squares on the edge GB1? Well, I can go with A1, so then there's going to be, this one is A1, GB1. And there's also going to be A2, GB1. And there's also going to be A3, GB1. So there's a book on this edge. But I can also go on one of the A edges. So who are the edges on this edge, G, A, G? Who are the squares? So with B1 I already drew it. What about with B2? So this is A2, no, A1, G, B2. And there's also this one, A1, G, B3. So, okay, I'm not going to draw the rest, but you see that on every edge you have this book. On this edge you have a book, on this edge you have a book. Yeah. Okay, and really for every pair from here, you're going to have a square. So really the squares that touch G, you can think of them as if they're in some kind of A by B matrix. Maybe it's better to draw the matrix like this. This is B1, B2, B3, and this is A1, A2, A3, and these are all the squares. Okay, so these guys are the endpoints. Every square has an endpoint that is not one of the neighbors of G, and the other endpoints are either G, AG, or GB. Okay, so in each one of these I have a square. These are all the squares touching G, and they're arranged in this matrix form. Okay. Okay, so let me define, so this is it, we define the complex. Now I want to define the code, and then we can take a break. So the code is essentially what we talked about earlier when we said let's do it on a simplicial complex. It's the same idea as in expander codes, where around the vertex you have a little code. Now we're going to have it around an edge. So fix some code CA, which is a subset of A bits. That's a linear code with a distance delta. Okay, I'll just write delta. So relative distance delta. And same for CB. Same thing. And now I'm going to define a code to be a two-chain, so a string that labels all the squares in my complex, so that around a B edge I have, for every little a, I have a square. So the bits that this B edge sees need to belong to CA. And around an A edge, the squares align according to B, so the bits need to belong to CB. So the code is going to be all the functions in 0, 1 to x2. Such that for every AG, F restricted to x2, let me call it. So remember in the expander codes I had this notation E sub V, which were all the edges touching V. Now I'm using this notation ad hoc to say all the squares that touch AG. You know what? Let me not write this way. For every AG I can just actually use this notation. F on the squares AG, and let me just put a dot here. So I'm thinking this ranges over all the B's in B. Okay, so this is a B bit string. It should belong to CB. And for every GB, F on GB with a dot belongs to CA. Again, A ranges here in A. This is an A-bit string and it needs to belong to CA. So that's the definition of the code. So it's like we said for the triangles. On every edge, you look at all the two faces around it and you require them to be in the code. So far, so good. But the nice thing here is that you get natural loops when you look from the point of view of a vertex. And I'll say that and then we can take a break. So what's going on here is that if F is in the code, okay, then let's look at F at the squares where I fix G, fix some G, and I let this run freely and this run freely. So I let A run freely in A and B run freely in B. Okay, so I'm going to now fill in the values of F in this matrix where A runs freely in A and B runs freely in B. And what I will see is that for every fixed A, I fix A here and I let B run freely, this belongs to CB for every single column. And for every fixed B, and I let A run freely, this is in CA for every fixed row. So what I get is that this is itself a tensor code word. Okay, so this belongs to the code which we denote CA tensor CB, tensor code. And I wish I could say recall, but I don't think I showed it in the lecture on tensors where I should have shown it, but we'll do it now. And tensor code words, these have constraint loops. Meaning, in a tensor code, there's many constraints that are linearly dependent. Okay, so that will be good. Right, we kind of want these things. So this will be good for us. Okay, let's take a break. Okay, guys, so now let's talk about tensor codes for a minute. So for those of you who maybe weren't here on the lecture that I talked about tensor codes, a tensor code is just, if I have two codes, or even if I have one, let's just focus on the case where I have one code on n bits, okay? And then we define the tensor code. It's a subset of 0, 1 to the n by n. So I'm now looking at n by n matrices where every column belongs to C and every row belongs to C. Okay, it's a tensor code. And you can, of course, have it different dimensions in C1 and C2. All right. And now, what does it mean every column belongs to C, every row belongs to C? So suppose the dimension of C is K. Okay, so the rate is K by N, and suppose also the distance of C is, I don't know, delta. Okay? Then it turns out that the dimension of this code, C tensor C, is K squared. And the reason is that you can take a K by K square here, put anything you want, and then you will encode, you can encode these, or there's a unique code word that will continue here. Okay, suppose it was a systematic code so that every message of K bits here can be extended. It's not always the case. Then you can encode every K bit into an entire message. And then once you have these K columns, you can encode every row this way, and you will get a tensor code word. Now, instead of proving it like, this requires proof, but instead of proving it, let's take it on faith. So the dimension is k squared, and the distance, sorry. So what is the distance of a tensor code? So if it's a non-zero code word, there's going to be at least one row that's non-zero. And in this row, there's going to be at least delta fraction of 1, so each one of those columns is going to be non-zero. So there's going to be at least delta fraction of non-zero columns, and in fact, for the same reason, there's going to be delta fraction of non-zero rows. So the distance is at least, it's equal to, well, delta squared times n squared, and at least delta n in non-zero rows, and the same for columns. Okay, so what is a natural parity check matrix for the code C tensor C? So suppose I have a parity check matrix for C. Okay, so suppose C itself is the kernel of H, and H is a matrix that is n by n minus k, n minus k by n. Okay, because the dimension of C is k, so the number of constraints is n minus k. This is H. Okay. Then, how many constraints do I have on this column? I have n minus k constraints, requiring this set of bits to be in C. What about this column? Same thing, n minus k. So the number of constraints I have on all the columns is really n number of columns times n minus k. These are column constraints. And I also have, for every row, I have n minus k constraints, because you need this set of n bits to be in the code C. So there's n minus k constraints. And similarly, this row and so on. So I have n minus k constraints times n rows. These are the row constraints. So a natural chain here will be to take the set of code word or strings and say, I'll write it in one arrow, and say that I have a parity check. This is like the tensor H. Let me call it H2. Okay, it's not this H. What is it? It moves me to n times n minus k times, or let me write it plus here, plus n minus k times n. So these are all the parity checks that we had here. Okay, but now I have another arrow. So it turns out that these constraints are redundant. How do I know that they're redundant? Because my dimension is k squared, and the ambient dimension is n squared. So really the codimension of the code is n squared minus k squared. But the number of constraints how many constraints do I have? This many. So that's 2n times n minus k. Okay, whereas this equals n plus k times n minus k. Right, so this is like n plus k times n minus k, and this is n plus n times n minus k. So this is certainly bigger. And in fact, how much bigger is it? It's exactly, this is equal to the codimension plus n minus k squared. So this is the amount of redundancy, or the amount of loops among the constraints. Okay, and these are the amount of independent loops among the constraints. So I can write in this chain n minus k squared. And actually, what will be this map? So who are these loops? So now from counting, we realize that there are some loops. But let's actually find them. Turns out it's something that we've already seen. So let me just draw the picture bigger. So this is a potential tensor code word. Let me have many coordinates so it's more fun. Okay, so this is my code word. And suppose there is some constraint on the column code that says that the sum of this, and this, these 3 bits always need to XOR to 0. So this means that also, these 3 bits need to XOR to 0 because this is the same code as this one, right? And also here. Okay? But, okay, so that's one type of constraint. And the other type of constraint is a constraint on the rows. So it could be that these 3 bits need to XOR to 0. And also these 3 bits need to XOR to 0. So, I will get, so suppose I call this constraint alpha and this constraint beta, just the subset of bits that need to XOR to 0. Okay, then let's look at the subset of bits that are alpha times beta. Let me erase these guys and erase these guys and just draw. Okay, so I just put the set of bits that are alpha cross beta. So this is a constraint, this is a constraint, and this is a constraint, but also the rows, right? So also this is a constraint, and this guy, and this guy. So I found now 6 constraints that sum to 0 in every tensor code word. It means that the last constraint is linearly dependent on the previous ones. Okay? That's really nice. So it means, like we discussed before, that if one of these is unhappy, there must be another one that's unhappy. Okay, just like we had in the consistoric expansion, like we had in the Hadamard code, which is the first code ever to be proven locally testable. So in the Hadamard code, you have some magic square argument, and the tensor code is really a generalization of that. And in fact, I would be very curious to find other arguments showing local testability. Somehow everything boils down to this, okay? And maybe this is partly why we don't know how to do it for simplicial complexes. The tensor structure is somehow something we already know. There are these loops in it, and I'm sure there's many other loops to be found, but we just don't know them. So anyway, what we see is that for every constraint for C, for every pair of constraints for C, we have a loop. And this is exactly how many constraints we have for C, n minus k. So for every pair, that's exactly how many loops. So we found all of the loops. These are the loops. So if we're lucky, these loops mean that there is some consistoric expansion on this chain. Okay? The fact that it's a 2 chain is just the fact that any code word, when you calculate the constraints, they will always cancel. Okay, it just means that this is a loop. So indeed, it's a 2 chain, and the fact that you have consistoric expansion, it's not always true, and this we discussed in the lecture on tensor codes. For many cases, you have consistoric expansion here, but we don't know exactly. This is still kind of not well understood. But let's pretend that we took, or let's take our codes, I don't know where I wrote them, CA and CB are over there, that are, for which this chain does have consistoric expansion. Okay, so then the theorem is that our graph, our code that we defined itself is a locally testable code. Okay, but I first want to talk about rate and distance like we talked for expander codes. Okay, so I'm going to first not talk about local testability, but rather we define this code. This is our definition. This is the definition of the code. Okay, we took 2 linear codes. Let's also add, suppose that they that the 2 chain has co-boundary expansion. It's actually co-boundary expansion in this case. In other words, CA tensor CB is locally testable. This is the way this should be read. And this is our code. And now let's first kind of look at it and try to understand what's going on. So how did we define the code? We said it's all two chains, such that around every edge the bits on the squares belong to these little subcodes. And it could be that this definition is empty, that there aren't, well, the zero function will belong to, is there, but maybe there's no more. So we need to understand the rate. And this is the same problem that, or issue that we had with expander codes. We defined, this was in the beginning of the first hour, we defined expander codes and we analyzed the rate. So let's do it for this code. So here instead of half we're going to do 3/4. And we say if the rate of CA and CB is 3/4 or above, then the dimension of our code, it's going to be linear in the number of squares. So the rate will be constant. And again, we just do it by counting. So let's do the number of degrees of freedom, or the dimension of the ambient dimension, is the number of squares. So how many squares do I have? I have G times A times B divided by 4. So remember in my complex, how many squares did I have? This was how many rooted squares I had, but then every 4 of them I combined into 1, so it's really this number divided by 4. And people came to me at the break and said, you know, but there might be some collapse. It's true, but let's ignore it. So you can arrange it so that there is no collapse. And in fact, even if there is collapse, it will still work, but let's not worry about it. Okay, how many constraints do I have? So I have a constraint for every edge. So that's the number of edges. For every edge, I don't have one constraint. Really, the number of constraints that I have is some 1 minus R naught times D, if the size of A and B is D. Okay, so really let me, instead of A times B, let me write D squared here. And how many edges do I have? So every vertex has how many neighbors? D squared, right, D squared squares touch a vertex. How many edges touch a vertex? Size of A plus the size of B, thank you. So it's 2D. So the number of edges is the number of vertices times 2D. Okay, so I have here D squared I have in both cases. Here I have 2 times 1 minus R0, and here I have divide by 4. So let's see. So the dimension is bigger than, let me write here, G times D squared divided by 4. So then here I put a 1. And here I want to have, I have D squared. I'm going to put divide by 4. And then here I guess I need to multiply by 8. That sounds bad.
No, but weren't you double counting?
I was double counting 2D, but I need to divide by 2, right? Because every edge is double counted. Okay, so then it's like this. Sorry, so it was like this, right? It's how many edges do I have? Usually it's the number of vertices times the degree divided by 2. The degree is 2D, divided by 2 is D. So this is the number of edges, and this is how many constraints on every edge. So I have GD squared divided by 4 times 4. So then what I get here is 1 minus 4, 1 minus R0, which is exactly the same as before, except I have a 4. Okay, so if this is bigger than 3/4, this is positive. Okay, so in our case it's positive. Not positive, I mean it's omega of E.
But you want there not the number of edges, but the number of triangles.
You're right, number of squares, correct. So it's not E here. This E was in black, it was from the other guy, right? So it's x2. Okay, so as long as this coefficient is positive, I get some positive constant times the number of squares. So we got positive rate. Okay, as for distance, okay, what did we do? What was the argument before? We said since the thing is linear, it's enough to look at the smallest weight non-zero code word, still the same. So let's look at such a code word. It's some leveling of the squares, and there is some vertex that touches some non-zero square, right? Okay, so since that vertex, the local view of this vertex is a tensor code word. What is the distance of this local tensor code word? Right, exactly. So I don't know what picture is best to look at. You fix a vertex, the squares that it sees around it, they belong to the tensor code where it's like CA times CB, where each of them has distance delta. So the distance of this thing is delta squared at least. And so any vertex that touches a non-zero bit must touch delta squared fraction, delta squared times d squared. So each vertex that is in V prime, yeah, it touches, it's true, it touches delta squared, d squared non-zero squares, but what I want to say is more. I want to say, and I wrote it somewhere, yeah, I wrote it here. Where did I thought I wrote it? No, okay, it got erased. If you are a non-zero code word, you must have at least delta fraction of non-zero rows and delta fraction of non-zero columns. So it means that the number of neighbors of this guy that also see something non-zero is delta. So it's the same delta here is still true. I want to maybe spend another minute on this. All right, so I'm in some vertex, and there's all these squares touching this vertex. Maybe it's best to think of them this way. So the vertex, I'm thinking of it, imagining it here, and these are like the neighbors of my vertex, B1, B2, B3, and A1, A2, A3. And now, there's some non-zero code word. So what does it mean? It means that some of the rows are non-zero, and some of the columns are non-zero. So if a row is non-zero, it means that not only G sees something non-zero, also GB, corresponding to this row, also sees something non-zero. It turns out that because, maybe look at this picture, which is more accurate. G has a neighbor GB1, and on this edge, there's all this row with the A's, right? So if this row is non-zero for G, it's part of the squares that touch GB1. So also GB1 has some squares that are non-zero. Okay, so it means that every V that sees a non-zero square has at least delta 0 times 2D, because there's 2D neighbors, neighbors that are also, they see non-zero. Okay, and this means that the distance is and then by the Alon-Chang lemma over here, you see that the number of elements in V prime is at least, let's see where it says 0. The number of elements in V prime is at least delta minus lambda. Okay, so there's this many vertices that see something non-zero, but how many squares? So now I need to multiply by delta squared. So previously I multiplied by delta. Now I multiply by delta squared because this is how many squares around the non-zero vertex are actually non-zero. So we get delta cubed. If lambda is negligible, you get delta cubed. Okay, so then the last and most interesting thing is the local testability.
Can you explain the delta squared again?
Sure. I first was counting how many vertices see a non-zero square. And by the Alon-Chang lemma, so maybe I should add here, by the Alon-Chang lemma, V prime is at least delta minus lambda times V. Okay, so now every vertex that is in V prime, how many squares does it see that are non-zero? So it's seeing a tensor code word and it's not zero. Tensor code words can be small, the distance is not delta, it's delta squared times d squared. So you think of this probabilistic process. You select a random vertex and then you select a random square in that vertex. The probability that you got a non-zero is at least this. Okay. So now maybe I do Okay, so now let's talk about local testability. So for proving local testability, I need to show that if I'm given any two-chain F, it always will satisfy this inequality, this systolic or co-boundary inequality that says that for any two-chain F, I want to have this inequality that the weight of, okay, let me say H, I don't think we had notation for this guy, H2 of F. So let this be the parity check of the code. So by this, what I mean exactly, what is the parity check of the code? For every edge in the graph, in the square complex, you have this bunch of checks. Okay, so this is the parity check. Maybe I should write. So what is this H2? Yeah. Yeah.
About what you said earlier about the Alon-Chang lemma. For that you need that some graph will be expanded. Can you say exactly what the graph is?
Thank you. Good catch. I used it, but who is lambda? Okay, good. Thanks. When we prove distance, we are using this lemma requires that the graph is a lambda expander. Every graph is a lambda expander. It depends what lambda is, right? So if lambda is 1, for example, you don't get anything, okay, or close to 1. Okay, so which graph do we need to be a lambda expander? The graph that I erased, the one skeleton of our complex, just the graph that connects G to AG and to GB. So so this is a condition for this whole thing to work. We want our Cayley graphs. Okay, we want our graphs to be lambda expanders. Let's just leave it at that. Okay, I think I'll just continue next week with the proof. So I'll now just do some setup and then we can do it leisurely next time. What is the parity check of our code? So this is my definition of the code. The code words are two chains whose length is x2. So this dimension is x2. And then how many constraints do I have? So the way I wrote it here, for every A edge, I have some number of constraints, and for every B edge, I have some number of constraints. So you can think of it that the matrix has two parts. This is for the A edges, and this is for the B edges. And then for every A edge, I have some bunch of constraints, like this, where here I put the parity check matrix of the code CA. This is HA, and for every, this I put the parity check of CB, and here I put the parity check of CA, and where do I put it? On the set of squares that touch this edge. So if this was an edge and it happened to be that I organized the columns so that these are the squares that touch this edge, then I write here HA. Usually it won't be continuous, it will be mixed around. Anyway, this is the parity check matrix. And what I need to prove is that the fraction of constraints that are unhappy, upper bounds beta, which is the local testability we wish to prove, times the distance of f to our code. Right, so this is our goal. This is our goal. Or let's say lemma. Or theorem, I don't know. Okay. Okay. So now the way we will do it is similar a little bit to how we did the decoding of the expander codes. We are given some f, we don't know anything about it. And now there's two things that can happen. Either we apply h to f and we see how many constraints are violated. Actually, no, I don't do it this way. Our goal is to say if few constraints are violated, then, they got hidden over here. Okay. Then we can correct f. So the goal is that if this is small, want to find f hat that's in the code, and f hat is close to f. This is our goal. Okay. Remember, what did we have when we did the decoding algorithm? We said if there were few errors, so there was some other condition. If there were few errors, we wanted to find this code word that's close to our f. And how are we going to do it? Well, the first step will be the same. So we have some algorithm. The first step will be every vertex. So we have a 2 chain. It's a bunch of bits written on the squares. What can a vertex do?
The best tensor word.
Exactly. This vertex looks at the bits around it, it organizes them in a nice A by B matrix, and it finds the closest tensor code word. Every vertex finds in the relevant code. And let's call this guy WV. Okay, so for vertex V, I let WV be the closest actual code word that's closest to whatever the local view is. Okay, so now I have a bunch of local views. It could be that they already completely match and everything is great, but it could be that they disagree with each other. I have no way of knowing. So now we want to understand what to do. So every time a vertex doesn't touch any unhappy constraint. So suppose we have a vertex that all of the local code word here, all the constraints that are on the edges touching this guy, all of them are happy. Then the local view of this vertex will be the same as the global code word. Okay, so the only times that a vertex will change is if this vertex sees some violated constraints. So if you are promised that there is very, very few violated constraints, think of some very small epsilon. It means that there's going to be only a few epsilon fraction of the vertices. And now I'm cheating a little bit because I'm changing between epsilon fraction of vertices to epsilon fraction of squares, but doesn't matter because it's a bounded degree graph. So there's going to be only an epsilon fraction of vertices that actually see something wrong, that their local view is not equal to the global thing. Okay. So this is what we should have in mind. Most vertices, their local view is already nice. Some vertices, they change the local view to make it nice. Okay. And now I'm going to do this kind of repeated correction things. So each vertex, we don't do it in parallel, in turn. So every vertex, there's some ordering. each vertex switches to agree with more neighbors. So what do I mean by this? Now we're again in this situation where every vertex has an opinion about its bunch of squares, but a square has an opinion from other vertices as well. So G looks only at its neighbors. It doesn't care about these guys, only at the D neighbors here and the D neighbors here. And he asks himself, what do all these neighbors want? You know, maybe if I change my local code word to something else, maybe I will agree with more of my neighbors. If so, I will do this change. My goal is to now minimize my local disagreement. Okay, so we have this initialization step, and now we're doing locally minimize the disagreement. Okay, so there is some underlying set here, E prime, of edges UV, such that WU disagrees with WV. Now, earlier I wrote, when we were doing expander code, I wrote WU of the edge UV is not equal to WV of the edge UV. But this is no longer relevant. Now, WU is a whole matrix of bits, and WV is also a whole matrix of bits, and how do they intersect? So maybe we can see it between G and AG here. This edge, there's a whole bunch of squares on which they intersect. It's like an entire column. So it's really like the vertex G has an entire matrix. The vertex AG has another entire matrix, and they intersect on this entire column. Okay, and with the GB guys, the intersection is on some entire row. Okay, so G will ask himself, you know, which of my neighbors agree with me, and maybe I will flip. Okay, and repeat. And then at the end, we'll repeat until stuck. And again, because of the same reasoning, when a vertex decides to flip, the local number of neighbors that disagree with him reduces. So it means that the global number of disagreeing edges decreases. So this means that there is some global potential function, which is the number of edges here, which keeps decreasing. So the number of times you do this is bounded, and you won't loop forever. And in the end, you say if E prime is 0, there's no disagreement, then output F hat. How do you know what F hat is? You don't have F hat. All you have is a bunch of local views. But since all the local views now agree, it's obvious how to define F hat. You just, on every square, you choose one of the endpoints and you take that value. They're all the same. So this is your algorithm. So we will analyze it next week. But you see how it's also similar to the algorithm we had for consystolic expansion, right? We had every vertex look at the triangles around it, and if there were more problems, it would change. So it's always the same thing of trying to locally do some, minimize some global potential function. And then use the expansion to show that you can't get stuck. So, I mean, if you got stuck and but you didn't reach 0, then there is some set of problems. These are the edges E prime. And we will use the expansion to show that, and something like the Alon-Chang lemma to show that, E prime must be very large. So, okay. Any questions? Okay.
So the strategy should be to bound the number of steps of the algorithm as a function of the number of original or as a function of the distance of the original x?
Oh, great question. So, right, so we have this algorithm. One main thing we need to prove is that if you started with relatively small amount of bad constraints, you will converge to a perfect code word. And the second thing you need to show is that this perfect code word is close to your f. So really, you will write here f hat, right? This is the f hat, and you need to show that this f hat is indeed, if the amount of rejection was small, this is the syndrome. So if the syndrome had small weight, few constraints are unhappy, then the distance needs to be small. You need to relate the distance to this. How will you do it? You say, what's going on in f hat? If a square, if you had some square, that all of the vertices touching this square started out as being perfect, so that the local code word was, they didn't need to change anything, and you never touched them throughout this algorithm, then of course f hat will be equal to f on this square. So then, which are the squares that can be different? Only those where either here you touched some problematic vertex, or sometime during the run of this loop, your vertex was problematic. So you're going to bound how many, this is bounded by the number of steps, this is also bounded by something, and
the idea that the original number of constraints was, violations was low will be somehow inside beta. So, because you said that you need the original word not to be too far away from
no, right, so that's a great question. So, unlike the case of decoding expander codes, this is a much stronger statement. This is also an algorithm that decodes, but it's under no promise whatsoever. There, you had to have the promise that only few errors happened. Here, there's no promise. This will always work. Either you will reach 0, or you know that the number of the weight was very large to begin with. So you're kind of saying either the weight is bigger than beta, in which case this inequality is satisfied because this distance is at most 1, or the weight is smaller than beta, and then you will prove that this algorithm converges.